if you all don't mind that I will record, and we're sending it to everybody else. We were sending it in emails, we're distributing it, putting it on a website, anywhere else that we can share this information, we're sharing. So welcome, and I will share my screen. And the way that we will do it today, and why is it here? Okay. The way that we will do it today, that we will, I will go through a presentation as we usually do. And then Anatoly will take over with a few examples and actually walking through a real use case. And hopefully we'll leave some time for questions. And again, because it's a small group, please interrupt me whenever you need. No problems with that. And yeah, let's kick it up. So today we're talking about a process functional modeling. Acronym goes as a PFM inside the platform, and the process functional modeling in action, what we call here. We usually start every presentation with some sort of quote. In this case, it's a dear Dr. Deming. Uh, when you're talking processes, Dr. Deming is probably the one of the most important people in the room. And he said, if you can't describe what you're doing as a process, you don't know what you're doing. And that's literally what we just discussed between four of us, that many people don't know their own processes, even though they work on these processes for years. So this tool actually help us to break through that lack of knowledge, understand the processes, and eventually actually solve the problem. Oops. Okay, so process function model is basically an analytical tool that helps us to understand the process. It models through various operations, help us to solve problems, identify the ways how to improve it. And this is just a subset, or I think the most important list of things that we think important to highlight what the process functional model actually gives us. Again, understanding how the process works. Many people, even though they work for years on the same process, they don't know enough details, right? Understand each operation. That's amazingly important because if you don't know what the operation does and what the outcome or what the product is, then how can you make any informal decisions, right? Analyze the same things and understand the contribution of each operation. Again, we will dive into that in a moment. Make a strategic and tactical decisions about how do we improve, how do we potentially cut costs and so on and so forth. And in my mind, William, what you just mentioned is to create this common language across the organization. As we well know, well aware, engineers speak in a completely different language than the management. And at the end of the day, the management starts demanding for different reports and different, decks like this one to even explain what the engineer does, right? Which is engineers hate, as far as I know, and all of that is happening mainly because the management doesn't necessarily understand the nitty and gritty of the engineer's language. Now, there's different use cases for that. Of course, designing a process. If you're designing something from scratch, very important. Improve existing one. I see that as almost the same thing. You design a new one or improving existing one, you still need to analyze what you're trying to achieve or what are you currently achieving, right? Reduce complexity of a process that eventually translates into cost, reducing the cost of the process, right? So the more complexity usually means more costs, more problems, more human errors, you name it, right? Improve process yield. Of course, it's related to complexity. So the simpler the process is, the less errors there are, the higher yield, and so on. Redundant and low value operations. We will dive into that in a moment. And many companies going through like Lean, Kaizen, Lean Six Sigma, and so on, different events. And these events, which is a little bit foreign concept for us, we think it's not supposed to be an event. It should be just a continuous process of improvement, right? And the fact that companies decide, okay, let's do, initiative of reducing cost. Well, it should be done all the time. But even though we are kind of promoting that as these kind of tools, they can be and should be used as part of these events, even the one-off events, right? I've been part of like efficiency week in one of the companies I used to work for. And the funny part that there was a bunch of ideas that actually none of them been implemented eventually. Now, let's talk about the process. What is the process, right? A process is eventually is a human-made system that is built to create something, create a product or create a value or increase the value, right? It receives an energy into the process, and the energy could be raw materials, like written here, electricity, information, anything that needed to actually for the process to work to produce the product, right? Then the process itself, the system is built to convert that energy, all of these inputs, from information to everything else into the product. And that means manufacturing equipment, computers, people, anything that actually does the work of that conversion. And then the product. The product could be something physical, it could be a value, but basically how we define the product, it's a carrier of a value, right? If we're saying that the process is built to increase the value, sorry, the process is there to increase the value of something, then the product is that value. Yes, sometimes it's a physical product. Now, if we dive deeper into the process, right, every process is built out of series of operations, right? Many times people describe a process as potential diagram, a diagram of a ramified diagram, potentially parallel tasks, and so on. We can describe it this way, but we see it as regardless of what you do and how you do it, it's a series of operations, right? And a series of operations, once you map that, then the question is, so it's great information to have once you have it in front of your eyes, but what do you do next with that, right? The question is, which operation should I improve? Which one should I potentially even terminate? And how do I reduce cost and so on and so forth. And the answer that we're coming up with the to this question is the process functional model is the tool to analyze. It's an analytical tool again to analyze and understand what do we do with all of these different operations and what the suggestions in terms of what to do with these operations. Now there are four types of operations. One is productive, probably one of the most important ones. Productive operation is something that adds value to the final product or to the final product. It's an irreversible change, and as an example here, like drill a hole or add something to the product, boil an egg, something that we doing to the final product in order to increase the value. Providing operations, uh, I think the easiest thing here is the example with the drilling hole, right? So the providing operation, for example, is marking a place where you're going to drill that hole, right? So it's not adding any value to the product, right? But that mark is going to go away eventually. But it is necessary so we do a precise job of drilling, right? So that would be example of providing operations. Other example of soaping the hand and so on. Photolithography from microelectronics. and so on. There is probably millions of examples of that. Corrective operation, again, uh, it's by the going by the example of drilling a hole, right? You drill a hole, now you have leftovers and uneven surface. Now you need to clean it up. That would be a corrective operation. Usually irreversible change to remove defects of the productive uh, pr- uh, productive operations or other operations, but usually productive operations, like drilling a hole, right? And then metrology. Metrology is part of kind of quality assurance, or are we measuring, did we do the work correctly? In a case of drilling a hole, did we actually drill it in the right place? Is it the right size? And so on and so forth, right? And many examples of that, especially in software engineer, it's a typical QA. In manufacturing, is their own QA processes and so on. Or in multi-step operations like semiconductors, we will measure parameters, very specific parameters inside the chip that gone through another step in the process. Now, here's an interesting part. The That's like a typical breakdown of these different operations. So we have productive, metrology, corrective, and providing. And normally, the productive operations do not exceed 20%, maybe 25, but that's a very rare. In semiconductors, it's typical to have 16%. But what does it mean? It means because productive operation is the only one that actually adds value to the product, everything else is waste of money, waste of time, waste of money, and so on. So looking at this map, the 16% is great, that's adding a value. Everything else is an opportunity for us to improve and reduce costs and so on. I'll pause here for a moment. All right. Now, let's classify, again, dive into different types of operations. So productive, again, just to remind, it's an irreversible change on an object or on a product, increase the final product's value. Normally, the strategy or strategic decision here should be improve or focus our efforts to improve the operation, right? To to make it more efficient, better yield, and so on. So if we want to invest any efforts into anything, we should invest it into productive operations, improve performance of productive operations. Providing it's a temporary change, right? It does increase the cost of the final product. There is nothing we can do about that. It never adds value to the final product because it is a providing, it's a temporary change. Eventually, it's not going to be part of a product, like marking the place of a drilled hole. Strategy, do not invest in that. Try to simplify or ideally eliminate these ones, and we'll see in a bit how. Corrective operations, right? These operations typically exist, as we mentioned before, because of the poor performance of productive operations or sometimes providing operations. It may or may not add some value, but if you think about that, if the productive operation was perfect, we wouldn't need that corrective operation, right? If the hole drilling wouldn't leave any leftovers, we don't need to clean it up. It's perfect, right? So again, the strategy here is don't improve it, don't try to develop them further, try to enhance the productive operations, and by doing so, eliminate the corrective ones. And then metrology. The biggest question is that we always need to ask ourselves, do we actually need these operations, right? It doesn't provide any changes on an object. We're just measuring, we're making sure that we did previous job correctly. There is no value added, and so on. So the biggest question, do we need them? And if we don't, And again, the analysis allow us to identify that if we don't need these metrologies, kick them out. We don't need them, right? Now, typical example of metrology, I came across that many of unneeded metrology. Sorry, I came across that many times in my career where there was a metrology in place that was put many years ago, but processes changes since then, and but nobody looked back and say, do we actually still need it, and just continue doing whatever they used to do. Again, part of the cognitive biases that each and every one of us each and every one of us have. So again, analyze and remove metrology if possible. Now, when we built as part of the functional modeling, in order to identify or analyze each and every one of the operations, we're building something called a functional model, something that we talked about last time. And this is where we're making the functional model helps us to make tactical decisions in terms of how we make the changes, how we actually solve these different problems, right? So if you think about it, the process functional model is more strategic, and functional model, or we call it officially system functional model, when you analyze each and every operation, this is more tactical, how you actually gonna achieve what you want to achieve. And that's about it for my part. I'll pause here for any questions if you guys have. And if not, we will dive into the actual demo with Anatoly.
How about,
Okay.
can you discuss the interactions between those systems? So like right there, you got operation 1 and operation 2. So you've got those broken down into process steps, but how those process steps are interrelated. So say you're deburring a hole, but you're painting it as well. And if you don't deburr it, then the paint doesn't stick to the burred edge, something like that. So I'm just familiar with other software that links those components and relationships to those components, that they're good or bad.
Right.
A burr is
Right.
bad.
So
Removing the burr is good, but now you've got to get rid of the burr waste product. So now you've got a waste product piece that could get into the rest of your, manufacturing process. So now that's a contaminant. So it's a good thing and a bad thing to get that burr out of there. That's why I was looking to see how you guys deal with relationships.
Right. So I must go a little bit back here, right? So process, and not necessarily for the process, but if you imagine yourself, this is one step of a process. Even a single step in the process will have an energy and will have a product, and then some system that performs that job, right? Now, the interrelation, basically the output of one step is the input of another, right? Now, the system doesn't link them automatically. It's a human being that needs to, while you model these things, it's the human being that needs to model it appropriately, so so we can take it further with the calculations, right? Again, there's nothing magical or automatic about that. It's the engineer who models these things needs to make these decisions on how to model each and every one of the steps, right? Don't forget that not necessarily, for example, let me go back to this one. For example, not necessarily the output of operation 1 in its entirety will go to operation 2, right? Some of the inputs from outputs from operation 1 will eventually be used in operation 3 and further, right? So for example, we're preparing a pattern on a microchip, right? It might not be needed on a second operation. It might need it further down the line, but it's been created on the first one, right? There's many examples like that. So the system automatically doesn't know anything about that. It's when you model it, this is where it comes into play, if it makes sense.
Okay.
And again, we'll have an example right now in a second.
Okay.
Any other questions before we dive in? All right, let's do that.
I send a request.
Yeah, I approved it.
Sure. Okay. Great.
It's still
So,
a black screen. Now we see. Yeah.
okay, great. So pick up some project, for instance, this one. It's very good example. I have a lot of examples. But first I want to show you how it operates. We go to the creative tools within the platform. We click internet is, we click list of tools. We have 12. You can see 11. This one, the 12th one, we're still working on this, and it will appear in 1-2 weeks, and we will make additional webinar about this tool. It's very good tool. So here is functional modeling. Here is process functional modeling. If you forget how to use it, you have this button, learn more, and you get to the documentation. Let's click, and we are in the tool. Here we can describe what system we're going to analyze, and we go to the model. Within the model, we should just create a process flow. Process flow. For instance, step 1, we can change title operation 1. Okay, save. And we can add another operation. For instance, operation 2, save. And so on. We can continue. The next step is to define the type of the operation. Again, it could be productive. We have to think, is it irreversible change, or maybe it's a temporary change, or it's corrective or metrology, and pick up something, and pick up something. Since we define type of operation, we can go inside of operation and within operation to create operation functional model. And we create model. Here we should define the product, components, function, another component, and so on. This component and that component, and we can have a look on the ranking. and so on. What's important here, we can, when we create next step, we can add new step, or we can copy existing step, because in many cases we are dealing with repetitive operations, and we can copy operation together with a functional model and so on, and after that to edit it. So I will return and show you example. We had a problem in microelectronics and semiconductors. Very trivial situation when we oxidize a wafer. Wafers are placed into the boat, and the boat moved into the furnace, into the hot furnace, 300, 400 degrees centigrade, and oxygen is added into the atmosphere to make silicon oxide layer. The problem is the bottom wafers are always affected, and standard deviation is 2-3 times higher than the rest of the wafers. And this furnace is created out of 3 parts of the furnace and managed by different thermocouples. Very trivial, and something happened. Again, we created process functional model. Here we describe the process, and we created flow. The first step is the preloading. This is loading of wafers within the boat. This is loading of boat into the furnace. Stabilization, we need to wait until temperature will be it's the same in all furnaces. This is huge furnace, 150 wafers. And after that, oxidation and unloading, when we remove the boat, cooling, and a measurement of the thickness. And we defined type of operation. And within each operation, if you go within each operation, you can see we created functional model. And by the way, we can version this model and try to modify it, and we can have a look on the ranking. And for each operation, we can see the most functional components and the most problematic components. So when we completed all this work, we can see first of all merit of each operation, which shows this is actually a ratio of functional rank and problematic rank. And we go to summary. Summary is made automatically, and we see here some main parameters of your process: productive operation effectiveness. This is related to productive operations only. Operation types breakdown, and we see only 14% is productive operation. This table reminds us that we need that the only productive operation actually adds value into the product. All the rest is wasting time and money. Therefore, the recommendation that system gives, if it's productive operation, consider improving. Think how to improve it. Apply new technology. Invest money, invest knowledge, invest into this operation. And if it's providing, consider eliminating. Think how to eliminate it. If it's a corrective operation, do nothing. Don't spend money and time for this operation. It doesn't make any sense. Yeah, when you improve providing operation and productive operation, and when you simplify or terminate providing operation, this operation, corrective operation, will disappear. Now, have a look on this very interesting picture. Let's return to the problem we tried to solve. We said the problem is the bottom wafers have very high variation. You see, all merits are green except two. Two operations are red. And what is the peculiarity of this operation? It is loading of the boat with wafers into the furnace or unloading. So these two operations, the only operations when we move wafers. What does it mean? That means that we create our problem during the movement of the wafers within the furnace. And this is what we found, and we created model. What's happened actually when we load this boat with wafers into the furnace, this first thermocouple sees cold wafers. And what does it mean, cold wafers? We cool down the first thermocouple, and thermocouple gives signal to bottom furnace increase power. And instead of to get real feedback, another cold wafer coming, and so on, so forth. And what's happened in the end of the process, the bottom part of the furnace is always overheated. This is the reason. This is the problem. And I've been working with an engineer from United States, from Oregon, from Portland. And he said, yeah, it's a very difficult instrument. We've been working very hard for 3 days. Really, we've been working for 3 days, and we found solution. And I said, how long have you worked on this problem before? He said 2 years. 2 years versus 3 days. And the difference, 2 years, he wasted time of company, and 3 days he was working hard and spent his time. So this is very good tool for effective understanding the process and solving. By the way, they try to redesign the flange in order to, and they spent 2 years and got nothing, because this is not systematic work. I want to show you one more example. I just started to work on this. Why it's so slowly? Let's see. I see. Yeah. This is also referring to microelectronics. But you know, examples what I'm talking about, you don't need to be PhD in semiconductors. This is typical chemistry. As always, I say chemistry is the same in different places. Salaries are different. And so the process, here is a process of a building interconnection layer. We had this layer and we should build this layer above this layer. How to do it? And of course, it's very, very long operation. I described it here in details, and we can go to the process flow. And this is the process flow. And again, we have here a lot of repetitive operations. Therefore, no problem to copy it and edit and adjust it. So let's go to the summary. And it looks good because I slightly simplified the flow. And in this case, it's 30%, about 31% of productive operation is on. The rest is operations that don't bring any value. So, and here we have all information and how to improve this process. And for instance, lithography is a typical providing operation. And when I see that companies replace lithography, previous lithography, which cost $70 million for EUV lithography, which cost $150 million, it out of sense. It's good for our lithography equipment producers, but it's not for chip makers. And we should think how to avoid, how to terminate lithography at all, because lithography don't increase value of the product. This is their fact. And
at the same time, one of the most expensive operations
exactly.
and equipments and so on.
And makes a lot of problems. Very difficult. So we should switch our mind. And this is a real innovation. This is real innovation. Because when we think about some improvements without usage any tools, we make systems more difficult, which is not innovation. Real innovation when we move into direction of simplification, when we simplify system, when we simplify processes. And you know, everything can be considered as a process. It could be a semiconductor, or it could be software making, or it could be purchasing in duty-free. Doesn't matter, it's process. And you can analyze it. And when you analyze it, you learn how this process operates, and you can improve it and make real innovations. So
one
that's
thing
all.
to add here.
Yes, please.
So we mostly talking about manufacturing in majority of our use cases. Somebody pointed out to me last week that if you take, for example, data center, right, something that not necessarily directly related to manufacturing at all, but data center is in a way a process, but your product is data, right? So even there, you can easily break it down into the process flow and start analyzing each and every one of the steps and understanding where you have inefficiencies and how you can improve it.
Can you show the function model for that photolithography?
Functional model of lithography?
Yeah, so
Yeah,
all
sure.
the components and the
Sure.
interactions.
Yes, yeah. For instance, this one.
Right, but Do you have one that shows the interactions between like move and with the verbs that say,
You
um,
see, you
that's what I'm
see,
looking for.
yes, yes, yeah. More than that, I already tried to verify it, version it, and we can try to simplify it. Our platform allows to make verification, to make uh, how to say it, Alex? Help me.
You can basically model your planned change and see how it will potentially perform.
Right. So that right
Right.
there to the whole team, that I don't know what you call that. I guess you call that a function model breakdown. Um, that showing it to a team is very, very powerful because um, we did that at not Ingersoll Rand, at General Electric gas turbine, and we had air
Hmm.
at the top where you have exposure chuck or exposure chamber. We had air as a component of a gas turbine. And we're like,
Hmm.
well, we make the gas turbine, we don't make air, God makes air. So air is on there as a component, but nobody cared about air. And then air had 50 arrows coming from it because all the parts were cooled with air. The
Mm-hmm.
smokestack was diluted with air. The smokestack was, particulates were knocked down with air. And the combustion process needed air. And every single component in our gas turbine needed air to cool it so it wouldn't melt. So we had hundreds of arrows pointing to air, and our manufacturing and our marketing people said, wow, that's pretty powerful. And, these guys were knucklehead marketing people, and they looked at it and said, we should be in the air handling business. We should not be just building gas turbines. If we want to build a gas turbine correctly, we should be supplying the air. We should be shoving air somehow into it. We shouldn't leave it up to, XYZ company who makes air handlers. And they immediately created a group in that gas turbine analysis team. The results were we need an air handling company or division or group part of the gas turbine. So yeah, we want to focus on the gas turbine and cooling
Mm-hmm.
all those parts, but we also want to do filtration of massive amounts of air and not leave it up to possibly one of our competitors who makes air filters and air handling devices. So that right there, that type of image is super powerful for a team to look at and go, oh,
Exactly.
I didn't know we cared about water.
Exactly.
Yeah, it's just
Yeah.
very powerful.
And
More than
you
that,
did
I always,
now.
yeah. Mhm.
Yeah, go ahead. Go ahead.
So, additionally, what we can see, I always explain, we have a product, and we typically have this is functions and goes directly to the product. They have name basic function. That actually functions we need. We need to create our pattern, but we are so stupid that we need so many components in order to supply actually this function. Guys, this is their way for innovation. What does it mean to innovate? To pick up component which is very far, which has low functionality and terminate it. Maybe delegate its functions to another component, but reduce component. When we reduce components, we improve yield, we reduce cost, and we innovate. This is the direction for innovation. And for
And we
functional
improve
model,
speed as well.
yeah, sure. Oh, of course. And a functional model shows exactly what to do. If you make lean, these are components you don't need. Don't think about these components. These components, they have very low functionality. Some components have functional and problematic rank. You can go to a recommendation, and in some recommendation, oh, just a moment, let me see. Oh, in some recommendations, you can see reference to 40 inventive principles. And you click and you get exactly to the 40 inventive principles, and it will navigate you to contradiction and to principles that are relevant to solve your problem, and guys, actually to innovate. We published it number of times, and we said innovation is ability to make profit from problems, from failures. This is their innovation.
And that another thing, William, what you mentioned when marketing were involved, I don't remember if I mentioned it at the very beginning, but about the common language. So it's not only between managers and the engineers, but it's also across the company. It's very, very important to have when people working on these functional models or process functional models or modeling anything really, it's very important to have different people from different departments in the same room. And we had a few examples of that where one of our clients, they were modeling their product or a piece of their product, and the marketing was in the room. And one of the things they said, well, it's all great. What you're proposing is great, but we can't sell it. Right?
That's all.
It just exactly the opposite example what you gave. Instead of coming up with, we might need to be a air handling company or department or something. They basically said we can't sell what you guys proposing, right? Which is a perfectly valid thing to have in these meetings.
Yeah, so what I normally do for building function models like this, I take a bill of material and I take a bill of
Hmm.
material for our current product. And when I was working in fuel nozzles, I would take all the components for fuel nozzles and each one of them would have a bullet item. And one of those problems with the fuel nozzles, we had 50 parts all welded together. And each time you took two parts
Hmm.
and welded it together, you had to have fluoropenetrant inspection, visual inspection, pressure test to make sure your weld was good. You had to have an x-ray. So if you could get rid of a weld in between those two components, then you were, it was key because you got rid of the weld. So you got rid of all the 4 or 5 different inspection methods that went along with that weld. So you could immediately put your current product into a function model and say, look, if we got rid of the welds and made a one part fuel nozzle, almost like a humongous car fuel injector, you could get rid of all those welds, all those parts, all those inspections, all those failure modes, all those places that are potentially can cause issues and break. And it was a monumental task to have everybody looking at that saying, wow, you got something there. You make a fuel nozzle with 1 or 2 parts and not 50 parts. You just, cut the cost to, half or a quarter of the cost of those parts.
Right.
Yeah.
And there is another piece that many times where groups, for example, engineers sitting and solving a problem, even though they did come up with an amazing idea, they go in with the management. The first reaction of management is being skeptical, right? Because they haven't been involved in the process of decision making itself, right? And management sees risk. That's all they see. in majority of times. It's like, oh my God, how do we implement that? Even though I've been told many times it looks great on paper, but what's the risk, right? But if we involving all the layers and all the people that related that may or may not be affected in these changes or proposals, and they again speak in the same language, all of a sudden it's much easier to accept this non I don't want to say non-trivial solution. Sometimes it's actually trivial but not obvious solution, right?
Mm-hmm.
Where like many times the solution is actually very simple and it looks very simple, and that makes people even more skeptical, right? How come we have so complex system and the solution for whatever we're dealing with
Right.
is so trivial?
Yeah, the risk management was very big, and that's the reason why there were so many different inspections of those welds. Because if a broken part
Mm-hmm.
went downstream in a gas turbine, it would corncob the gas turbine. A little metal part would
Yeah.
take off a big metal part, and then before you know it, you had a $20 million boat anchor with no blades on it. You basically
Yep.
had one little tiny $100 weld break loose and it just killed an entire gas turbine. So yeah,
Yep. Yep.
risk management and being able to see if you got rid of welds and got rid of those risks, you could save yourself a lot of money.
Yeah. All right. So, guys, you can see a lot of examples here in our hub. We have hub where real projects are published. If people, it's mainly my projects and my students' projects. You can go inside of the project and have a look. It's about 50, 60 projects or so. Another thing I want to show you, we have a newsletter in LinkedIn where people don't like to read, unfortunately. I like to read very much. Therefore, I started to write funny stories about problem solving using problem solving tools. And it's the title is Sinkman Chronicles. It's already today I published a new one about these are all real stories. Real stories, how problems were solved. Again, this is physics and chemistry, not necessary to be PhD in semiconductors to understand it, but it's something that happened mm, in everywhere, metallurgy and so on. Read it. I hope you will like it. I can share
We can
this.
send it. We will send it
Okay.
in
We will send
together
it
with the email.
with the email. Read it. It's really funny story. Guys are sitting and talking how Moore's law impacted everywhere on all our life. This is a real story. So if you have
Great.
questions, I would be glad. By the way, if you need my help or Alex's help, our help, uh, let us know, and we can do it.
All right. I'll stop the recording.